This is section 11.1. Title of the section is Lines that Intersect Circles. These are the objectives. You can pause it and read it. I'm just going to go to the next slide. This is the vocabulary you're going to be responsible. You can pause this as well and read it. I'm going to continue to the next slide. Let me go over these terms. First one is a chord is a segment whose endpoints lie on a circle and is highlighted there in red. The second term is a secant is a line that intersects a circle at 2 points, is highlighted there in blue. And a tangent is a line that in the same plane as a circle that intersects it at exactly 1 point. This is very important to understand. It only they intersect exactly 1 point, unlike the secant that they intersect at 2 points. And the point of intersection in the tangent is what they call a point of tangency. Is where the point, where the circle and the line meet, where they intersect. The only point of intersection. Let's go with this first example. It says identify each line or segment that intersects circle P. Talking about identifying chords. These are the two answers. Refer to the definition. It should make perfect sense. Secant, ST. Again, refer to the definition. Tangent, SUV. And let's highlight the point of tangency for fun. So this will be the point of tangency. A single point of intersection between the circle and the tangent UV. Diameter, we know this from a previous section. It's ST. And radii, again from a previous section. You're looking at PQ, PT, and PS. Next slide. Pairs of circles. These are pretty straightforward terms. The first one is congruent circles. If you look at the diagram, it makes perfect sense. I'm not going to highlight it. You can look at this picture. And like I said, it will make sense. Concentric circles. Look at the picture, and it should make sense what concentric circles represents. And then also the last one, tangent circles. Number 2, it says identify the point of tangency and write the equation of the tangent line at this point. So the first thing is to identify the coordinate value of this point. And we know that is equal to 2, -1. The second part is to identify the equation of the tangent, which is this horizontal line that you see here. And from algebra 1, we know that it represents y equals -1. Let's go to the next slide. Common tangent is a line that is tangent to two circles. Let's highlight the first common tangent. Line L and M are common external tangents to circle A and B. And the next one, lines P and Q are common internal tangents to circle A and B. Circle B. Let me highlight something about these two definitions. If I was to connect the two centers of the circle, notice that the external tangents do not intersect this segment. Same idea, connect these two centers with this segment, and notice that these two tangents do intersect that segment. So there's a difference between external tangents and internal tangents. First set of theorems. Theorem 11.1.1 says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So in other words, if you have a tangent to a circle, the radius and the tangent line, they form 90 degrees. They're perpendicular. And you're going to notice that 11.1.1.2 is a converse of 11.1.1.1. So you can read this, pause this, and read this more carefully. I'm going to the next slide. Next theorem says if two segments are tangent to a circle from the same external point, this is the external point that they're talking about, then the segments are congruent. This distance, AB and AC, are congruent. Theorem problem number 3 says HK and HG are tangent to circle F. Find HG. The theorem that we just saw, which was theorem 11.1.13, says that these two segments are congruent. By definition of congruence, we can write equality. So we have that HK is equal to HT. From here we do a substitution, we cross multiply, and we get x squared is equal to 10x. We review algebra. Since we have a quadratic, I want to move everything to one side, 0 on the other side. Factor the common factor of x. You have the following. We apply the zero product property, and this is what you get: x equal to 0 or x equals 10. And of course, we're not going to be using this one, otherwise we get for HG get nothing. So we use x equals 10. We substitute. Since HG is equal to 5 times x, we substitute x, and that's how we end up with 50. Problem number 4. It says RS and RT are tangent to circle Q. So the same idea, we apply the same theorem, 11.1.3. We have RS is equal to RT. Substitute. 6x equals x squared plus 9. Another quadratic. Move everything to one side. We factor this. We get the following. Now notice that the two binomials are the same, so it wouldn't make sense to set both of the binomials equal to 0 since they're going to generate the same x value. So we just do x minus 3 equals 0, and then we end up with x equals 3. From here we substitute to find RS, and RS equal to 6x, so 6 times 3 gives us 18. Problem number 5 says in each diagram AB and AC are tangent to circle O. Find each measure. And again, we saw a theorem earlier that said that these two lines are perpendicular, so they form a 90-degree angle. Same thing here. This was theorem 1.1.1. So these two are 90. And this is a quadrilateral, and a quadrilateral equals to 360, so you know that this angle and this angle is equal to 180 if you take away the two 90s. So we have the following equation: the measurement of angle O plus the measurement of angle A is equal to 180. We substitute the value of angle A. We solve for angle O, and this is what we get for angle 110 degrees. Let's go to part B of this problem. Same idea. I know that these two are 90 degrees, so I have measurement of angle O plus the measurement of angle A is also equal to 180. In this case, I'm going to substitute these algebraic expressions for each of the angles, do a little bit of algebra. Solve for x, and you get 92. I'm looking for the measurement of angle A, so what I need to do is I need to take away 6 from 92, and that's how I end up with measurement of angle A, which is 86 degrees. Problem number 6 is assume that the segments that appear to be tangent are tangent. Find CB. First thing we're going to do is we're going to call this x. Then we know that CA is equal to CB plus PA. This is the segment addition postulate. We substitute. We know that CB is equal to x, PA is equal to 7. And then at this point, we know that AD is equal to 7 and CD is equal to 24. Remember, AD is equal to 7 because the distance from here to here is also a radius. So if this is 7, this has to be 7. At this point, not only that, you should see the right triangle. So we can apply the Pythagorean theorem. CA squared plus CD squared CA squared equals CD squared plus AD squared. We substitute. This is what we get. I'm not going to do anything with the left hand side. I am going to square the 24, which is 576, and the 7 squared, which is 49. When I add those two numbers, I get 625. And then at this point, I'm going to take the square root of both sides of this equation. You did that in Algebra 1. On the left side, I get x plus 7. The square root of 625 is 25, so that's how we end up with plus or minus 25. From here, we should be able to find x, and we're going to be getting two x values. This 18 and negative 32, how do we get 18? From 25, we take away 7, and from negative 25, we take away 7. And of course, the only answer that we're going to work with is with positive x values. We don't use this one, and that's why the answer to CB is equal to 18. Let's go to the next slide. This is the last problem. Same directions as number 6, and they want you to find QS. Again, we can write this equation because of theorem 1, 1, 3. These two distances are equal. We substitute, we get 2y. These two distances QR and QT are equal. And also QS and QU, but let's just focus on this one first. So we solve for y, a little bit of algebra, we get y is equal to 3. Okay, so we still haven't answered the problem QS. So what we're going to do now, like I mentioned earlier, I know that QS is equal to QU by the same theorem, 11, 1, 3. At this point, I know that I can write the following. QS is equal to QT plus TU. Because QS is equal to QU, I can write this statement. I'm using the transitive property of segments. At this point, I substitute. I get 15 plus 4y for QS. I already found out what y is equal to. I substitute, and this is the answer, 27. This concludes 11.1.